Most people imagine the ocean as endlessly alive, filled with fish, movement, and ecosystems stacked on top of each other from the surface down to the seafloor, but there are vast regions beneath the waves where nothing large lives at all. Where fish vanish, predators never pass through, and even scavengers avoid the area because the water itself has become uninhabitable, and the unsettling part is that these places are not rare, they are not ancient, and they are not theoretical, they are expanding right now beneath shipping lanes, fishing grounds, and coastlines humans depend on. A dead zone in the ocean does not mean absolute emptiness, but it does mean something far more disturbing, because it means the water contains so little oxygen that complex life cannot survive there, which turns entire regions of the sea into biological voids, where only the simplest organisms endure, and everything else either flees or suffocates. To understand how this happens, you first need to understand that oxygen in the ocean does not come from the water itself, it comes from the surface, from the atmosphere, and from microscopic plants called phytoplankton that live where sunlight reaches. Which means oxygen is constantly being added at the top and slowly consumed as you go deeper, creating a delicate balance that only works if the ocean keeps circulating and mixing. In healthy oceans, surface water rich in oxygen sinks and deeper water rises, allowing life to exist at many levels. But when that circulation weakens or stops, oxygen becomes trapped near the surface, while deeper layers are slowly drained dry by bacteria, decay, and respiration, and once oxygen drops below a critical threshold, animals cannot survive regardless of how much food is present. This is where dead zones begin, not suddenly, not violently, but quietly as oxygen levels slip just low enough to make survival impossible. One of the most important distinctions scientists make is between natural oxygen minimum zones and human-driven dead zones, because not all low oxygen areas are new, and not all are caused by pollution. But the difference between them explains why the modern ocean is changing so rapidly. Natural oxygen minimum zones exist in parts of the open ocean where circulation is weak and productivity at the surface is high, meaning a lot of organic matter sinks and decomposes, consuming oxygen faster than it can be replaced. And these zones have existed for thousands of years in places like the Eastern Pacific and parts of the Indian Ocean. But even these natural zones are expanding today, growing thicker and spreading horizontally as the ocean warms and circulation slows. Human-caused dead zones, however, are far more aggressive and far more alarming because they form rapidly and often appear in coastal regions that once supported dense fisheries and thriving ecosystems. The process begins on land, not at sea, when excess nutrients from agriculture, sewage, and industrial runoff are carried into rivers and eventually dumped into the ocean, where they act like fertilizer for phytoplankton, triggering massive blooms that look productive at first but set the stage for collapse. These blooms eventually die, and when they sink, bacteria break them down, consuming enormous amounts of oxygen in the process, and if the water column is stratified, meaning warm surface water sits on top of cooler deep water and prevents mixing, oxygen cannot be replenished fast enough, and the system suffocates. This is exactly what happens every year in the Gulf of Mexico, where a dead zone forms that can cover an area larger than entire countries, forcing fish, shrimp, and crabs to flee or die and creating a seasonal underwater desert beneath one of the most economically important fisheries on Earth. The Baltic Sea tells an even darker story because there the dead zones are not seasonal. They are persistent, covering large portions of the seafloor where oxygen levels have been low for decades, creating sediments that release toxic compounds like hydrogen sulfide, further poisoning the environment and preventing recovery. In these zones, even organisms adapted to low oxygen struggle to survive, and complex ecosystems collapse into microbial dominance, where bacteria that do not rely on oxygen take over and fundamentally alter the chemistry of the water. The Arabian Sea hosts one of the largest oxygen minimum zones on the planet, stretching across hundreds of thousands of square kilometers. And unlike coastal dead zones driven by runoff, this one is shaped by monsoon cycles, productivity, and circulation patterns, yet it too is intensifying as warming reduces oxygen solubility and slows mixing. What makes dead zones especially unsettling is that they are invisible from the surface because ships pass over them, storms move across them, and waves break above them as if nothing is wrong, while below, life has simply vanished. Fish often detect these zones before humans do, abandoning traditional migration routes and spawning grounds, which can cause fisheries to collapse even when no overfishing has occurred, leaving communities confused as to why once reliable stocks have disappeared. Some species attempt to survive at the margins, stacking themselves along thin layers of water where oxygen is just barely sufficient, creating a natural crowding that increases predation and stress, while others are forced into shallower waters where they become easier targets for fishing. As oxygen levels drop, the ocean does not just lose animals, it loses functions because many essential processes like nutrient cycling, carbon storage, and food web stability depend on oxygen-breathing organisms, and when those organisms vanish, the system becomes simpler, more fragile, and harder to restore. Dead zones also interact with climate change in dangerous ways because low oxygen environments favor microbes that produce greenhouse gases like nitrous oxide, which is far more potent than carbon dioxide, turning dead zones into amplifiers of atmospheric warming. Warming itself worsens the problem because warmer water holds less oxygen and increases stratification, making it harder for surface oxygen to reach deeper layers, creating a feedback loop where dead zones expand simply because the ocean is getting warmer. This is why scientists are increasingly concerned that dead zones represent not isolated problems, but early warnings of a broader shift toward a less oxygenated ocean, one where large areas become hostile to complex life, not because of pollution alone, but because the basic physics of the ocean are changing. What makes recovery so difficult is that once oxygen is depleted, the chemistry of sediments changes, locking phosphorus and other nutrients into forms that continue fueling blooms even after pollution is reduced, meaning dead zones can persist long after the original cause is addressed. Some regions have shown partial recovery through aggressive nutrient management and improved wastewater treatment, but these successes are fragile and easily reversed, especially as warming continues to tilt conditions toward oxygen loss. Perhaps the most disturbing aspect of ocean dead zones is that they force us to confront a misconception we rarely question, which is the idea that the ocean is too big to fail, too vast for human activity to fundamentally alter, when in reality, its life support systems operate on narrow margins that can be pushed past breaking points faster than we expect. The ocean does not collapse loudly, it collapses quietly by losing oxygen molecule by molecule until one day entire regions become places where nothing large can live. And the only sign at the surface is the absence of what used to be there. Dead zones are not the ocean dying everywhere at once, they are the ocean sending warnings in specific places, showing us what happens when circulation slows, nutrients overload, and oxygen disappears. And the fact that these zones are growing should tell us something important about the direction the system is moving. The ocean has always contained extremes, but it has never been empty by accident, and when life disappears from the water, it is not because the ocean chose silence, but because the conditions that supported complexity were quietly removed.